All right, so let's start the second part of the problem solving. For chapter 6. So let's start with problem number 10. Okay, so what we have here. So it says that we have a dart of mass this. Okay, is pressed against the spring of a toy dart gun as shown in the figure. The spring with the spring constant, so K is also given. Although is compressed to 6 centimeters. So this is the displacement and released. So if the dart ditches from the spring when the spring if the dart from the spring when the spring reaches its natural length, what speed does the dart acquire? Okay, so let's try to understand the problem. So here we have a dart gun. Okay, this is the dart. The mass of the dart is given and the spring constant of this spring is also given. So we compress this spring. Okay, so this is our initial position. So we compress the spring to 6 centimeters. So this is probably the equilibrium position. So we compress from this equilibrium position to this point. So this is 6 centimeter. Okay, and at this point all the energy here we have is stored in the spring. Okay, and the dart is at rest. So the initial velocity for this dart is equal to 0. Okay, so this is 6 centimeters. So this distance is 6 centimeter. Okay, and the initial potential initial velocity is equal to 0 for this dart. So here at this position we have kinetic energy that is equal to 0, right? Because the v1, the speed, is equal to 0. We have the potential energy, and in this case, because we are dealing with a spring, the potential energy will be half kx square. Okay, remember that this is the elastic potential energy, not the gravitational potential energy in this problem. Now when it released, okay, when the spring is released, okay, then it come back to its original position. It come back to its equilibrium position. Okay, so when it come back to its equilibrium position, x equal to 0, right? So when x equal to 0, potential energy will be equal to 0, because half kx square and x equal to 0 means so this is basically 1 and this is 2. Okay, so because x2 equal to 0, potential energy, the elastic potential energy at this position will also be equal to 0. The kinetic energy will have some, because the dart now will be moving with some speed v2, so we'll have the kinetic energy, and that is equal to half mv square. And again, if I neglect the air resistance, we can write that ke2 plus pe2 equal to ke1 plus pe1. And again, this is very simple, because pe2 is 0 and ke1 equal to 0. And then we have half m v2 square equal to half kx1 square. So half and half cancel out. v2 square equal to k by m x1 square. So v2 is equal to square root of k by m x1 square. Now k is given 250 Newton per meter. M is given 0.100 kilogram. And then x is given 6 centimeter. Okay, 6 centimeter means this meter, 10 to the power minus 2. You have to convert this one to meter, right? So centimeter to meter is by 10 to the power minus 2, and then square. So then we have a square root on top of everything. Okay, so this gives me the speed of the dart is 3 meter per second. Okay, so again you see that the here we use the conservation of mechanical energy. All right, the next problem. All right, so in the last few problem, we use either gravitational potential energy or elastic potential energy separately. But this is the problem where we are going to use both together. Okay, so I mean, this equation, the conservation of mechanical energy could be something like this. Okay, and this could be then PE1 gravity 1, PE elastic 1, and then PE elastic 2. So instead of 2 terms, we may have 3 terms. Okay. All right. So here we are going to use both potential energy in this problem. Okay. So let's see. So the problem says that we have a mass we have a ball whose mass is 2.60 kilogram. Okay, so it is at rest at this position. So at this position, it is at rest. That means the kinetic energy at this position is equal to 0. But there is a potential energy, gravitational potential energy, right? Because it is at some height. So it will be mgy1. But at this point, there is no elastic potential energy because the spring is at its equilibrium position. So the elastic potential energy at the position 1 is equal to 0. And then you drop the mass, drop the ball on the spring, and because of that, it compressed by this amount. Okay. So now again, the ball is at rest. So kinetic energy is again equal to 0. But here we have both potential and both potential energy. Okay, G2 equal to mgy2, and then elastic 2, that will be half kx2 square. Okay, now then the conservation of mechanical energy will be ke1 plus peg1 plus pel1 equal to ke2 plus peg2 plus pel2. Okay, but the good thing is this is 0, so let me erase it. This is 0, let me erase it. This is 0, let me erase it. So it's very simple now, only 3 terms. Okay, so now let me write down one by one. So pg1 is mgy1, this mgy2 plus half k x2 square. Okay, we have to basically calculate k. We have to solve for k. Okay, so because we have to solve for k, let me take the k in one side. But before I do that, let's try to understand the height, the meaning of y's. Okay, so let me erase these things. Okay, now here, this is our reference line. Okay, so y1 is basically this height, so it's fine. Y1 is equal to h, so that's good. How about y2? So let me write h. How about y2? Y2 is this height. Okay, and you see it is below, the this line. Okay, so because it is below this line, the value will be negative. Okay, so mg minus y. So the question says is this is y equal to 15 centimeter, but remember to use a negative sign because it is below the reference line. Okay, and x2 is also negative y, but here it doesn't matter because we are going to square it. Okay, but this negative sign is important. Okay, so what we have here, okay, now if I solve it for k, I can take it in this side, then it will be mgh plus mgy. So k will be 2 mgh plus mgy, and then it will be y square. So then it is 2 mgh plus y, and then y square. 2m is 2.60 kilogram, g is 9.80 meter per second square. Now h is 55 centimeters, so 55 times 10 to the power minus 2 meter, and y is 15 centimeter, so 15 times 10 to the power minus 2 meter. So we already taken care of the negative sign here. Okay, so we are done. Now we just need to plug the values. Okay, and y square is 15 times 10 to the power minus 2 meter, and then square. Okay, so then just plugging all these values in your calculator, and if you do it correctly, it should give you something like this: 1585 Newton per meter. So the spring constant for this spring is 1585. So here it looks like a little bit difficult when you I mean determine whether this is negative or not. Okay, so this is negative, this value is negative. I mean this y, this capital Y is negative. Okay, I mean we have to put a negative sign in front because you see that the y is below the reference line. Okay, so that's why here it's also use a negative sign. Okay, so because of it's negative, so we put a negative sign here, but this negative is not that important because we have a square. The square cancel the negative. Okay, but this is important. So then if you do the algebra correctly, you should get the spring constant for this spring is equal to 1585 Newton per meter. All right. All right, so it's very similar to one of the problem we did in the last class, but here we are going to use the friction. We are include friction. Okay, so far we did not I mean we neglect friction or the work done by the non-conservative force in this chapter. So now let's see what happens if we include friction here. Okay, All right, so it says that the car in the figure reaches a vertical height of 25 meter on the second hill. Okay, so in the first hill is 40 meter from the ground, the second hill is 25 meter. Okay, where the car car is basically okay, so the car in the figure reaches a vertical height of 25 meter on the second hill before coming to a momentary stop. So the car stops here. Okay, so if it traveled a distance 400 meter, determine the thermal energy. So it says that if it is moving, if it's starting from position 1 to this position, if this distance is 400 meter, what is the thermal energy? Okay, what is the thermal energy produced due to the friction between the car and the track? Okay, all right. So similar to all other problem, here this is our position 1 and this is our position 2. At the position 1 we have only potential energy, no kinetic energy, because the car starts from rest. Okay, here at this point again there is no kinetic energy because the car stops at this position. So in both position, in position 1 and 2, kinetic energy is 0. Okay, so now the conservation of energy. So this time we have to use the conservation of energy because we include non-conservative force, right? So the equation is something like this: ke2 plus pe2 equal to ke1 plus pe1 plus wnc. Okay, good thing is this is 0, this is 0. Okay, so pe2 is mgy2, pe1 is mgy1 plus wnc. Okay, so what is wnc? WNC, first let's calculate WNC. WNC is equal to mgy2 minus mgy1. Okay, so mgy2 minus y1, so 1000 kilogram, 9.8 meter per second square, and y2 is 40 meter, sorry, y2 is 25 meter, 25 meter minus y1 is 40 meter, right? So because you see this is y1 and this is y2, so that's why y2 is 25 minus 40 meter. So if you do this calculation in your calculator correctly, you should get a negative value. And non-conservative work, I mean work done by non-conservative force is always negative. Okay, remember that. So this, the work done by non-conservative force is this one. Okay, so now it asks us to calculate the to determine the friction force. Okay, so in the theory class you already know that the friction force by the non-conservative, the work done by the friction force is something like this: FFR D, right? Because the friction force and the displacement, the direction of the angle between the friction force and displacement is 180 degree, and that is negative, so we have these. Okay, so here in this equation you see that you can cancel this and this. Okay, actually cancel this and this, so FFR is 147,000 joule divided by D, and the question says D is 400 meter, right? This is 400 meter. So our estimated friction force is 300 147,068 Newton. So if you divide 147,000 joule by 400 meter, you get 368 Newton. So the friction force we estimate here is 368 Newton. Okay. All right. All right, so this is the problem about force, power. The next three problem is about power. So let's try. All right, so this question asks us to determine the power output for a 60 kilogram woman who runs up a 300 meter high flight of stairs in 3.5 seconds. Okay, starting from the rest, having a final speed of 2 meter per second. Okay, so this is our initial position. Okay, and this is, I mean, this is her initial position, this is final position. Initially, she does not have potential energy because height is equal to 0. Kinetic energy is also equal to 0. Okay, so here potential and kinetic both equal to 0. At this point, we have both kinetic energy, that is mgy, sorry, this is 2 y2. We have also kinetic energy because she is running at 2 meter per second at this position. So half mv2 square. Okay, so the change in change in energy, okay, is delta E is equal to final energy minus initial energy. Okay, so initial mechanical energy is 0 because both are 0. Okay, so it's basically E2, and E2 is basically PE2 plus KE2, that is equal to half, mgy2 plus half mv2 square. Okay, so the change in potential, change in energy, if you plug the values, so it is 60 kilogram and then 9.80 meter per second square. Y2 is 3 meter, right? So it says the 3 meter Y2, and then plus half, again 60 kilogram, and V2 is 2 meter per second square. So delta E is, if you plug all these values in your calculator correctly, it should give you 1884 joule. Okay, so the average power will be delta E over T. So delta E is 1884 joule, and T, the time is 3.5 second. So the average power she used is 538 watts. Okay, so you see that the power is the change in, the rate of change of the energy. Or so in this problem we use the energy. In some problem you will see that we have to use the work done, work divided by the time. Okay, for example, in the next problem we are going to use work done, I think. All right, so 2 more problems in this chapter. All right, so it said the estimate the power expended by a weightlifter raising a 150 kilogram of barbell 2 meter in 3 seconds. Okay, so let's say this is the barbell. Let's say this is the barbell at the ground. Okay, So here its ground is at rest. Okay, so kinetic energy is equal to 0, potential energy is also equal to 0. Okay, now the weightlifter lifts its 2 meter. Okay, let's say this is 2 meter, so it says 2 meter. So when it is here, it is again at rest, so there is no kinetic energy, but there is potential energy, PE2. Okay, PE2 is mgy2. Okay, so again, similar to the last problem, you can find the change in energy. So the change in energy is basically the change in the potential energy, right? So PE2 minus PE1. So PE2 is mgy2 and PE1 is equal to 0. So let me cancel it. So the power will be delta E over T. So that is equal to this. Now, what is the barbell's mass? It is 150 kilogram. This is 9.80 meter per second square. The height is 2 meter and time is 3 seconds. So this gives us P equal to 980 watts. Okay, so the power the weightlifter used here for this barbell to lift by 2 meter in 3 seconds is 980 watts. Okay, all right. All right, so this is the last problem. So I'm going to do only the first part. So try the second part by yourself. Okay, all right. So here we have a car and we have to calculate the power of the car whose mass is 1200 kilogram. Okay, to climb a 15-degree hill. So this is 15-degree hill. Okay, at a steady 90 kilometer per hour. Okay, so 90 kilometer per hour, and you know that 90 kilometer per hour is 25 meter per second. In one of the earlier problem we convert it. So yeah, so I just wrote down this 90 kilometer per hour is 25 meter per second. Okay, so what is the power it needed? Okay, provided, so we have one more line to add for this problem, for the problem number A. Assume that the average retarding force on the car is 700 Newton. So retarding force means the force acting on the car in this direction. So car is moving in this direction. A retarding force means that, for example, air resistance is a retarding force. So there is a force by the air resistance that is opposite, okay, opposite to the car's motion. So that means the retarding force. So if the retarding force is 700 Newton to climb a 15-degree hill, what power the car needs to use? Okay, so that's the problem. So let's try to solve. All right, so to solve this problem, the first thing is we have to do is draw a free body diagram. So let's say this is the car. Okay, okay, so this is the hill. Okay, and this is 15-degree, and let's say this is the car. So we have gravitational force mg. Okay, and we have also normal force. Normal force is normally perpendicular to the surface. So Okay, so this is the normal force. And if this is theta, we already know that this will be theta, right? And then because mg is no longer along, is neither along the x or y axis, normally this kind of problem we use this as our y-axis and this as our x-axis. The direction of the motion is basically the direction of the positive x-axis. Okay, so because the gravitational force is neither along x and y, we have to break it. So we'll have one component in this direction, right, and one component is in this direction. Okay, so this will be mg sine theta and this will be mg cosine theta, right? So recall that adjacent is related to cosine theta, opposite is related to the sine theta. So this is opposite, this is sine theta, this is adjacent, so this is cosine theta. Okay, so we break mg into its component. And we also know that the retarding force is in this direction. So this is retarding force. Okay, so you see that the car needs to push, or car engine needs to apply force in this direction. Okay, so what minimum force it requires? So it requires this amount of force, because you see that the opposite of this direction, we have this retarding force and also this force. Okay, mg sine theta. So opposite of the car's motion, we have two components. Okay, so the opposite of the car's direction, car's motion, we have this force plus mg sine theta. These two forces we have in the direction opposite to the car's motion. Okay, and what is this force? This is 700 Newton plus car's mass is 1200 kg, and then gravity is 9.8 meter per second square, and then sine 15 degree. Okay, so all together it is 3744 Newton. Okay, so to move upward, okay, so to move upward in this upward means to uphill, the car engine needs to provide at least this amount of force. Okay, car engine apply this, needs to apply this amount of force, okay, to move uphill. Okay, if the force is less than this, it cannot move move uphill. Okay, so what is the power then? So in one of the theory class, we determined the power can be expressed as the force and the velocity. So the force is here 3744 Newton and the velocity is 25 meter per second. Okay, so the power the car engine needs to provide is this is a very big number, 93593 watts. Okay, so to go uphill, okay, with this condition, this car needs to provide use this much power. Okay, so I just did the first one, so try the second one. So I already posted the solution, classwork solution, so go through it and try to understand this. If you have question, let me know. So I'm going to stop it here. Next class is about linear momentum.